Yeah, hello everyone. I was a little late here. Sorry, because all of a sudden Zoom is acting up on me. I've been having one of those weeks where every piece of technology I touch is turning into crap. Um, I have two PC laptops here, and one day last week I was trying to have a meeting, and and on both of them Windows crashed on me. So that just shows you how things have been going here. So to strike back, I actually bought a MacBook Pro, although I haven't set it up yet. So I'm going to have three computers now, and we'll see if between the three of them, one of them can be working at all times. And so today, all of a sudden, I noticed Zoom is not working correctly anymore. It's arguing with me about my password. So I have the right one. I send it in, and it says, no, that's not right. You'll have to reset it. And when I try to reset it, it says, oh, you're in. So it's just a typical week in the life of technology. Anyway, so we're back. That's what matters. I have to remind myself, by the way, real fast to make a note to get Zoom fixed. I'll add it to this very long list of other technological nonstop problems that I have. But anyway, oh, and the other day, my cell phone was giving me a fun time. One day it announced that going forward, it will not charge past 80% anymore. No reason, it just won't. And then a day later, it was back to charging normally. So you don't know what's going on with this crap. So that's why you have to have multiple ways of getting anything done, because at any given time, if you've got just the one, it's going to let you down, guaranteed. All right, that's my say for today. So anyway, what I want to do is get back to chapter 4. So I want to quickly review 4B, since even though I made a recording for that last week, I still want to go through it again, and then we can pick up with 4C. And I believe somewhere along the way, I posted an announcement about the midterm. It's, of course, as you know, the midterm is based on the first 3 chapters. It's not due for quite a while. I want to make sure you have plenty of time to do it. So let's go back and quickly look at Zoom, Moodle, if it will allow us. Yes, here we go. All right. Hold on one second. Yes. So yes, of course, there was no class yesterday because it was the 4th of July. The 14th. I was feeling very generous that day. Yeah. So you have until Bastille Day to do the midterm. And of course, you know, if you have any issues with it, you can send me questions by email. I made sure that, you know, I wanted to write a test that was pretty covered what we did, but not get too ridiculous. Some of the problems on the sample midterm were really out of control, I thought. So I made sure that none of the questions are ridiculously hard, but they do, you know, they cover the material and they're a little challenging, but just not to the point where you're spending an hour on each question. We don't need that. I just want to make sure everyone's getting the basic concepts. So I think you'll find as you're going through this thing that it's not going to be, well, at least it'll be straightforward. And that's really what I'm aiming for. All right, so let's get back to where we were. So yeah, I just want to quickly run through 4B again, even though you know, you had the opportunity to watch the video. I just want to go through it again. Some of this is very technical. I mean, they're introducing some important theorems in calculus. The reason why they're doing this now is because what they're doing is they're essentially showing you the justification for a lot of the results that we'll need. You know, math is one of those disciplines where everything we do has to be justified. Because in other words, in order to make a simple statement like When we find the first derivative is equal to 0, then we may have found a minimum or a maximum. We have to be able to demonstrate why that is the case, why there aren't any exceptions to that rule, for example. Why is this always true? And so if we can formally prove that these results always hold, then we can have some confidence in our results. And so when you get to a higher level of math, then they'll start asking you to actually prove some of this stuff. But at the moment, we're just learning the techniques, but it's also important to understand what's going on behind the scenes with a lot of these results that we're using. And we will have some applications here in this chapter, and we'll see more about how and when these results are useful. What we're essentially doing here is learning how optimization processes work. And optimization is something that can be useful in any discipline. For example, if a company is producing products, it's important for them to understand how many they should produce to maximize their profits. I mean, that's really why they're in business. And so with these techniques, we'll be learning, it becomes possible to do exactly that. And in fact, if you've ever had any economics classes, you'll see that, at least in micro, we often use calculus to help us find, for example, the profit maximizing output or the point that minimizes our costs. So, economics is heavily based on calculus. It lends itself well to optimizing functions. But luckily, in discipline like economics, we don't tend to get very bizarre functions. Like we don't tend to run into trig functions. We don't get, all these other bizarre ones. The functions that we see there tend to be very well behaved. Often they're polynomials, and that makes it a lot simpler to optimize them. All right, anyway, I need to do one thing here. I want to be able to use my tablet. So in order to do that, I'm going to have to pop out one of my hard drives. Hold on one second. And now let's see if I can do this. All right. It seems to have worked. Very nice. What do you know? All right. So I only have so many USB slots here, so I have to pop something out in order to use my tablet. All right. So the mean value theorem is something that enables us to carry out a lot of our optimization calculations. And so it's basically, we're actually going to start with a special case of the mean value theorem called Raleigh's theorem. And basically what it's telling us is that if we're looking at an interval, not the entire function, but an interval, in such a way where, let's see, let me draw a little sketch in here. It doesn't matter what the function is. It can be as bizarre as you want, but if we can identify or restrict our attention to an interval, the key detail here is that the function has the same value at both of these points. So in other words, f of a equals f of b. Okay, so what Raleigh's theorem is saying is that, with that being said, there must be some point in this interval where we have the slope of the function at that point, the derivative or the slope of the tangent is equal to 0. Okay, so in other words, we're guaranteed, what it basically means is we're guaranteed to have at least a relative maximum or minimum somewhere within that interval, as long as f of a equals f of b. Okay, now for other choices, like here, for example, they're not equal, are they? No. So we have no way of knowing. It means that, I mean, it's still possible that there is a relative maximum or minimum in there, but there's no guarantee of it. Whereas with this one on the left, this tells me that I can find at least one, maybe more, but at least one extreme point. And of course, we can find it by setting the first derivative equal to 0. All right, so that's kind of good to know. Now, in the book, they have some really nice examples of this, which are much cooler than my picture. And you can see in each case, they're showing us a graph. In the first two cases, there's one relative extreme point. On the left, the very first graph, part A, we have a relative maximum. In the second one, we have a relative minimum. And in the third case, we have one of each. C1 and C2, they're finding them there. And there's actually, in principle, no limit to how many extrema we can have in a given interval. Again, as long as it's the case that f of A equals f of B. Okay, so sometimes the challenge with finding these optimal points is that we're not sure if they exist in the first place. So with a theorem like Raleigh's theorem, knowing that the point exists can help us make it easier for us to find it, especially for terribly messy functions. Later on, we're going to see a special technique called Newton's method, where the point of it is to find optimal points when we're dealing with an unusually messy function. You start to, like, Newton's method is part of a branch of mathematics called numerical methods, where you're really trying to accomplish certain goals as quickly as possible, because possibly you don't have enough information about the function itself, or there could be other things going on, but it's a very useful technique for finding optimal points, especially when the function itself is unusual in some way. So here it's pretty straightforward because these are clearly all polynomials. So formally, now of course there's always a very formal statement. F of x is a continuous function. It has to be continuous. If there's any holes in there, that means that we may not be able to find an extremum, sorry. And also, if you notice, the function itself is continuous over the entire interval. If you notice those square brackets, that means we include a and b. It only needs to be differentiable, though, everywhere in between those 2 points. In other words, it's not absolutely necessary for it to be differentiable at a and b, so that you could actually have, like, let's say here, something like that going on, and yet still find an extremum in this interval. So the function will be continuous, and differentiable, of course, simply means that the derivative exists everywhere in that interval from a to b, but not necessarily including a and b. The most important detail is right here. Without this, the whole thing falls apart. And so we're guaranteed at least one critical point in there, which guarantees that there's a minimum or maximum in there somewhere. It could be a relative minimum or maximum. It could actually be the global minimum or maximum too, but we know that it exists. So here's one. F of x equals x squared plus 2x. And so we can demonstrate that Raleigh's theorem holds over the interval -2, 0 by actually identifying that point. Let's see, did I draw the picture here? There it is. Yes, I did. Okay, so this is what it looks like. Now, it's just a straight ahead parabola. Remember, we're only interested in the region between -2 and 0. Okay, which is what you're seeing here. I guess, all right, I'll shade it in here. Now, the key detail here is that f of -2 is 0, and so is f of 0. And, you can think of this as point A and point B. And you can prove that just by plugging them in. So if A is -2, f of A is, you just plug that right into the function. And you can see that it is in fact 0. Same thing with B equals 0. So we're all set there. Now, what we want to do is find where is that critical point. So of course, the way we do that is take the first derivative and set it equal to 0 and identify the value of C at which this is happening. So based on the power rule, let's do a quick review of the power rule. If we have something like this, where K and N are both constants, you're basically multiplying the entire expression by the exponent, and then you are subtracting 1 from that exponent. And so what that means then is that for something like x squared, keep in mind that there's an implicit 1 here. The K is 1. So that actually reduces to 2x, okay? For 2x, remember there is an implicit exponent of 1. So you add 2x to the 0, which is just 2. Okay, so you add them together, set it equal to 0, and you can solve for x equals -1. So at -1, oops, so I've upset the computer here. At -1, the slope will be of the first derivative is 0. Okay, so let's go find that point. Now, it just so happens when you plug in -1 into this function, we get -1. So the critical point is -1 comma -1. Okay, so I drew that, sketched that in here. Well, no, not that one. Right here, -1 comma -1. And now what we can do is take the first derivative and evaluate it where x equals -1, and we should get 0. Oh, keep doing the wrong thing. So yeah, so remember, we found that the first derivative is 2x plus 2. So since f of x, f prime of x is 2x plus 2, f prime of -1, and yes, as we guessed, this is 0, and so that tells us that this is a relative minimum. Now you can prove, by the way, just because you have a critical point, remember we have to be able to demonstrate whether this is a relative minimum or maximum, or possibly neither. Remember, that's a possibility too. We can use either the first or second derivative test, but here we don't need to do either because we have the graph. Okay, so in other words, we demonstrated that within this interval, there exists a relative maximum. Well, though in this case, it's an absolute maximum at the point -1, -1. And that's because at that point, the derivative has a value of 0. The slope of that tangent line is 0. So in other words, we know that it's there. We still have to find it ourselves. But it's comforting to know that no matter what interval we chose, literally any interval we chose for this function, as long as f of a equals f of b, we're guaranteed one. Okay. Well, now the mean value theorem is the same. It's like a bigger, broader version of this. What you're really looking for here is to show points where, if you look at this graph real quickly, we're guaranteed that we're going to have a tangent line with the same slope as the secant line that connects the two endpoints. So you can see in the graph, A and B are the endpoints. You'll recall from an earlier chapter, the slope of the secant line rather is f of b minus f of a over b minus a. Whatever that slope is, we're guaranteed to find a point in this interval where the tangent line has that same slope. So this is a more general version of Raleigh's theorem. Now, we're not going to actually use this for anything, but it's, it's important to understand it. But now here's another function, x squared, the square root of x rather, it looks like this. And so if you look at the interval 0, 9, now, this is still the mean value theorem. Okay, so these 2 points do not, f of 0 and f of 9 are not equal to each other. So we're using the full mean value theorem here. We're not using Raleigh's theorem. In fact, I'll tell you what, if you look at this function carefully, you'll notice something interesting. There's never going to be 2 points where f of a equals f of b. It can't happen. In fact, there's a special name for what we're seeing here. If you notice that even though it's increasing at a decreasing rate as we go to the right, no matter what happens with x, when x goes up, y always goes up. It's not always the same amount, of course, but no matter what, when x goes up, y goes up. A function like this is said to be monotonically increasing. And because it is, that guarantees that there's going to be no points where these two are equal. And so we're not going to find our extrema. Okay. All right, anyway. But in this case, so what we're going to do is evaluate the slope of the secant line between 0 and 9. All right, well, it's not perfect, but you get the idea. Remember what a secant means. It means we're connecting the curve in 2 different points. And so what we're going to do is first figure out what that slope is using the function. So because the f of x is the square root of x, f of 9 is 3, and f of 0 is just 0. So we've got in this ratio 3 minus 0 over 9 minus 0, which is a third. Okay, so the slope of this secant line is a third. Now we need to find the point in that interval where the tangent line has a slope of 1/3, and we're guaranteed that it exists. It's out there somewhere. We just have to find it. But it's not hard because all we're going to do is take the first derivative of the function and set it equal to not 0, but 1/3, because that's the slope that we're aiming for. And then we'll just need some algebra. Okay, so now remember, so this is the square root of x. What you probably should do with these radical signs, I always convert them immediately into fractional exponents. I just find it easier that way. I mean, when you're done, you can turn it back if you want. But it's easy to forget. Radical x is just x to the 1/2, and based on the power rule, our old friend, the power rule. See how often this shows up. Whoops. So if you started out with x to the 1/2 power, remember there's an implied 1 here. 1/2 minus 1 is -1/2. And so you could actually rewrite this as 1/2 radical x, because x to the minus 1/2 is 1/x to the positive 1/2, which means 1 over radical x. Okay, so then you also have this 2. So this is our final result. So this is what we have to set equal to 1/3. Okay, so anyway, so in the book they use the c, it's c or x, whatever. It doesn't really matter. It's 1/radical 2 c now. We're going to call it c. And we'll set that equal to 3. And so the algebra is on the next page. So, you multiply both sides by 3, you multiply both sides by 2 radical c, divide both sides by 2, and now we end up with 9/4. Now, you may or may not be able to tell just by looking at it, but it simply tells me. By the way, I just want to point out that when you take a square root like this, there are actually, if you want to be technical about it, there's 2 solutions, plus and minus 9/4. But we don't need the minus 9/4 because the interval that we're considering is only from 0 to 9. Okay, so in other words, the negative 9/4, we can discard it because that is not inside this interval. So in other words, what we just showed is that the critical point is 9/4 for x. It turns out that the function has a value of 3/2 at that point. And so the slope of this tangent line and the secant line are both the same. And we knew that it had to exist because of the mean value theorem. Now, by the way, a lot of these theorems, they start to build on top of each other. There'll be more theorems later on that are based on the premise that the mean value theorem is correct. So proofs are like a building block approach. You start out by saying, well, given that the mean value theorem holds, we do the following. It's almost, maybe I wouldn't compare it to Legos, but maybe I would. It's like there are pieces that you're building on to come up with a more complex structure. And so, in other words, these theorems are not just useful for demonstrating that what we're doing is correct, but also for enabling us to develop more advanced proofs. So it is very much a building block process. So maybe that analogy with Legos is a good one. So anyway, now, why is this so important? Because it means that we're guaranteed that within the interval that we chose, as if the first derivative is always positive without exception, then the function must be increasing in that interval. And if f of prime of x is always negative, then that guarantees that function is decreasing over that interval. We don't have to check every single point. We know that this is true because it's a consequence of the mean value theorem. So that example with the square root from 0 to 9, I did say before, monotonically increasing, we know that it's increasing without exception because the first derivative is 1 over 2 radical x. And there's no value of x between 0 and 9 where this would become negative. Okay, so in other words, we're guaranteeing that the function has a first derivative that's positive at every point in this interval. And that implies that f of x is increasing throughout the entire interval. Okay, so that's all we needed to know. And of course, if you notice too, we don't need the whole function. There could be, for some functions, there could be ranges within which it is increasing or decreasing, but within an interval where we're guaranteeing ourselves that the first derivative is always positive, then we can say with certainty that the function is increasing. And of course, the opposite case would be something like this. And whatever this function is, we're guaranteed that it's decreasing. We choose an interval over which the first derivative is always negative. So here's a simple one. What if it was something like this? The first derivative is -2. No matter what interval we choose, the function will be decreasing in that interval. It's guaranteed. Okay. Well, that's good to know. So now here's a graph that came from the book. You can see look how easy this is. everything up to a, the function is increasing because the first derivative is always positive. And between a and b, the function is decreasing because the derivative is always negative in that interval. And then we have, once again, the function is increasing all the way up to infinity, it appears, because the function, the first derivative is always positive. Okay, well, then that means we can use derivatives to help us understand the shape of a graph, at least over different intervals. And so this is what makes it possible for us to have the first derivative test. Okay, so by the way, here's some very important graphs that we'll need. If you notice in the top, both of these curves are set up so that the first derivative is always positive, no matter where we are in that interval a to b. So the function is increasing. Same thing is true on the right, but what's different between the two is that on the left, we say that this function is increasing at an increasing rate. In other words, it's getting steeper. Over here, it's increasing at a decreasing rate. Now, we will see later on that you can distinguish between the two cases by the sign of the second derivative. The second derivative is the one that lets us know what's happening to the first derivative. Is it changing? Is it going up? Is it going down? Down here at the bottom, both of these functions are decreasing. So the first derivatives are always negative, but here, the curve, it's like if you're rolling, this is like coming down a very, very steep hill. This one is decreasing at an increasing rate, meaning it's getting steeper. It's like you're accelerating as you go down that hill. Here you're decreasing at a decreasing rate because it's flattening out. It's like you're slowing down as you go to the bottom of that hill. So I guess if you're a skier, it's the one on the right that you're aiming for. You don't want to be in the one on the left because otherwise by the time you hit the bottom, you're going 100 miles an hour. But yes, so these are 4 basic shapes that we will run into. And we're going to make the following statement now. A function continuous. Now, by the way, almost without fail, these results depend on continuity. If a function is continuous, that's fine. But if a function is discontinuous, often these results do not hold. So we have to be careful to make sure it's clear that this is a continuous function. So what we can claim now is that if the function is rising and then falling, that means we must have reached a maximum point. So over here on the left, we have a positive first derivative. Over here on the right, we have a negative first derivative. So we can tell that we must have reached in the middle here a relative maximum because the slope went from positive to negative. This is the point where it switches. And I'm sure you can imagine what's coming next. If we're at the bottom here, like the bottom of a parabola, if we can observe that along here, this derivative is positive, and over here it's negative, the point where it switches signs is guaranteed to be a minimum point. We can't tell from this if it's a relative or absolute, but we know that it's a minimum. And it should be clear just by looking at the picture. It's almost like you're just going to the top of a mountain or the bottom of a valley, I guess. Now, here's an interesting graph. This is where we're going to see this. Now, what they've done here is they have shown us all the points. These are all critical points, by the way. Remember what that means. A, B, C, and D are all critical points. And remember, that by itself doesn't guarantee that these points are extrema. If you notice, for example, f prime of A is undefined, but it's still an extremum, by the way. F prime of B is a relative minimum. F prime of C is neither. Now you can see, despite the fact that the tangent is flat there, guess what happened? The reason why this is not a minimum or a maximum is because the sign didn't change. The slope is positive on either side of that point. And that's really why this is no longer considered to be a relative maximum or minimum. It's a critical point, but it's not either a minimum or a maximum. It's just neither. But over here, with this one, in spite of remember, when a function has like a sharp break in like this, the derivative is undefined. The derivative requires that function converge to the same point from both directions. And that isn't happening here. So, but the signs are changing. And so therefore, this is in fact a relative maximum. So really what's giving it, letting us know, the critical points, you can think of as just candidates. They might be relative maxima or minima, but they don't have to be. And the way we can confirm it is with these sign changes. So all of this is collectively known as the first derivative test. The idea that we can identify our maxima and minima by looking at the way the first derivative changes on either side of that point. That's all we need to know. We don't need to evaluate the function at that point. This is enough to prove it. So yes, so you notice we in no point do we use anything other than the first derivative. So this is the first derivative test. Is one way to identify relative extrema. Okay. All right, so this is what we've been discussing. The first derivative will let us know if it's changing from one sign to the other. That means we must have found an extrema. All right, let's look at a quick example of this. Now, this is a cubic function, so it might have more than one extrema. In fact, it probably will. Those cubic functions have, this is a pretty standard look for a cubic function. So it should be pretty clear. We're looking at this point. Now, sometimes with these symbol lab graphs, it's hard to be sure. They're not all labeled. Looks like these are 4s. I think this is supposed to be 1 comma -1 comma 4. And this is supposed to be 3 comma -28. But we'll prove it. I mean, I'm just trying to tell by looking at the graph. Even symbol lab graphs, they don't always label them as well as they might. But we'll see. So anyway, I did go ahead and pay for the premium version. So if we need to look at some of their more advanced results, we can do that. So we're going to find the first derivative of this function. And again, based on the power rule, we end up with 3x squared minus 6x minus 9. So since we're looking for extrema, we'll set it equal to 0. Now, at first glance, you might say, oh, this looks like a mess. Not really. Look, we got lucky here. Look what we can do. We can divide out both sides by 3, and now it looks like we could actually factor this one. Certainly, we can always use the quadratic formula, but here, let's factor it. And so that's going to give me x minus 3 times x plus 1 equals 0. So that implies that the 2 points we're looking for are x equals 3 and x equals -1. I believe, yeah, that's right. So then, of course, we can figure out what the values of the y's are. So we've got 3 intervals. Think of this function as being broken up into 3 intervals. Everything to the left at this point. Jesus. All right, let me see if I can do an actual straight line here. Yeah, I know people who are basically graphic designers, and they do this stuff all the time. They must be awfully good. All right, that'll have to do. Think of this as like region 1, region 2, and region 3. So now, in principle, we can pick any point we want in region 1 to find the sign of the first derivative. So I chose the point. And these are the intervals. So for the first point, I chose -2. It could be any point in that first interval. And so that gives me a first derivative of 5, which is clearly positive. Well, I mean, we can see that from the graph, but it's good to confirm it. It just means that the function is increasing everywhere up to that point. And then you need a derivative, it's the interval number 2. And I've chosen 0. Remember that second interval was -1 up to 3. So by choosing 0, I end up with a negative, which clearly it is. You can see that the function is sloping downward in that second region. And then in region 3, which is 3 up to infinity, I chose 4, and that it has a positive value. And again, you can see that from the graph. No problems there. And so what we've done is identified these 2 points as extrema. More specifically, we know that the point -1, 4 must be a relative maximum, and that 3, -28 must be a relative minimum, because the sign goes from positive to negative. That makes this a maximum, and then it bounces back to positive, which guarantees that this is a minimum. Okay. So it's pretty straightforward, at least with polynomials. I mean, if we're looking at like cosines, and it can get very messy, but the logic is simply that when the sign goes from positive to negative, it's like reaching the top of a hill, so to speak. You go up, you hit the top, and you start to come down. That's a maximum. With the negative to positive, it's the other way around. You hit the bottom, and you start to go back up again. You must be in a valley, let's say. Okay, so yeah, I did some more sketching here. All right, now, of course, we're not done yet, because we want to incorporate the second derivative. And just keep in mind, the second derivative is the rate of change of the first derivative. And so we're going to introduce 2 very important new concepts based on the second derivative, and they are concavity and points of inflection. Now, again, this is only true. We're going to assume that we're looking at an interval. And if within that interval, the first derivative is always increasing, or increasing, then the function is concave up. So I'm going to show you a graph of this in a second so you can visualize what this looks like. If it's decreasing, which by the way, I just want to, and this is why we need the graphs, f prime of x doesn't have to be positive to be concave up as long as it's increasing. Okay, so that's kind of confusing until we see the graphs. F prime of x, it could be positive and yet decreasing. So in other words, with what we're doing here, all we need to know is increasing or decreasing, not positive or negative. So what does this actually look like? All right, so remember before we were talking about how this first graph is increasing at an increasing rate. That means, in other words, it's getting steeper. It's like you're climbing up a hill that's getting steeper. That means, although they haven't mentioned it just yet, the fact that the first derivative is getting higher as we go from A to B, that means that the second derivative is positive. Okay, because remember, it means the rate of change of the first derivative. So if the first derivative is increasing, the second derivative is positive. That is what we mean by concave up. Okay, now in the right, remember before we were talking about how here the derivative is increasing, but it's increasing at a decreasing rate. And because the first derivative, like I said, it's positive, but it's declining, we're going up a hill that's getting flatter. Okay. So that means the second derivative is actually negative, in spite of the fact that the first derivative is positive. The fact that it's decreasing, it's becoming less positive, means we have a negative second derivative, which is another way of saying that the function is concave down. Okay. Now, by the way, I just want to point out, up and down, some books don't use this terminology. You may have heard of this. Concave up is sometimes referred to as being convex, and concave down, in some books, they simply call that concave. I just want to mention that. In the book here, we're calling it up and down, but you may run into that term convex. And that's simply what it means. Convex is another name for concave up. Anyway, down here we have a slope that's negative, but it is getting less negative or increasing. That might be confusing. The slope is getting less negative, which implies that it's increasing. So we say that it's decreasing at an increasing rate. And that implies that the second derivative is positive. And so once again, we're going to call that concave up. And then finally down here, we have decreasing. Oh, wait a minute. I think I wrote it wrong. No, I'm sorry. I got it backwards. I wrote the wrong thing. Sorry. In other words, it's becoming less negative. In other words, it's like -4. Hold on a second. Let's say the slope is -4 here, and now it's only -2. So the first derivative is actually increasing, but the function itself is shrinking at a decreasing. It's not getting more negative. That's better. But that does mean that the second derivative is positive. Okay, I wrote the wrong thing over here. And then here, this is decreasing at an increasing rate. Concave down. second derivative is negative. Okay, so anyway, these are the four cases you might run into, and then all functions can contain regions where it's one or the other, or any one of the four. So we need to be able to identify within a given interval which one we're looking at. Now, yes. Oh, by the way, I drew these in here myself so you can just to see visually what's going on. Concave up, remember, is the same thing as convex in other books. And concave down in some books is simply referred to as concave. But you can tell by geometry, just by drawing a secant line through the function. So you notice here, the secant line is always above the function on either side of these. And that's what we mean by concave up or convex. When it's the other way around, when the line here, the secant line is below the function at all points, that's concave down or just plain concave. Now, in practice, like a classic example of this is bonds. If you've ever run into bonds in any of your travels, the relationship between bond prices and interest rates looks a lot like this one, okay? Because what's happening is that high interest rates lead to lower bond prices and vice versa, but in a very specific way. And so if you were to plot out that relationship, it would look something like this. I don't know any other examples offhand of these other functions, but I know for sure this one describes very well the relationship between bond prices and interest rates. Now, how do you test for concavity? In other words, we don't want to be always looking at graphs. I mean, it's nice to look at graphs, but we need to have a more formal approach to finding where we have a concave and a concave up or down function. And so we're going to take the second derivative. Now, by the way, we have to assume that the second derivative exists throughout the entire interval. Otherwise, again, none of this means anything. And if the second derivative is positive, as I showed you here, concave up is associated with the second derivative being positive. Concave down is associated with the second derivative being negative throughout the entire interval. Now, the inflection points is, remember, we introduced that term in the beginning. An inflection point is a point where the second derivative changes sign, or you can think of it as the concavity switching from up to down or down to up. So before, remember, in some of the graphs, we were interested in finding places where the first derivative changed signs. Here, we're looking for points where the second derivative changes signs, and these are known as inflection points. So here's a good example of this. We have a relative minimum and a relative maximum. But if you notice, the first derivative is switching from negative to positive right here. But throughout that entire interval, the second derivative is positive. So that, remember, was called concave up. And then all of a sudden, something changes. The second derivative is negative throughout this entire interval. Now, you can tell by the signs of the first derivatives that this is a relative maximum. And this is a relative minimum. But here, what we're really interested in is the fact that, right about here, we go from concave up to concave down. And that means that this is an inflection point. Now, there's no guarantee that there will be an inflection point in any given function, but it's important to find it because that means we know that the second derivative's behavior is changing. And it also means we may be moving from a relative minimum to relative maximum, but it could also mean we're going from a relative maximum to a relative minimum. Okay. It's kind of like, I mean, imagine yourself, let's say you're a skier, you start here, you're going down this incredibly steep hill. You're going really fast for a while, and then you start to go up, and all of a sudden your momentum starts to slow down. And from this point on, you're slowing, and you're just reaching the top. And then, oh no, you're going off to the races again. You're going downhill very, very quickly. All right, here's another one. We're going to take this cubic function and determine all the intervals where the function is concave up, concave down, and identify all the inflection points. So here's what it looks like. It's a typical cubic function. And you can probably visualize after what we just saw that since we have a relative maximum here and a relative minimum here, the inflection point would be right about here, let's say. Although we'll need to do the calculus to find the exact point. So actually, an inflection point can occur, strangely enough, not just when the sign switches from the second derivative. It's also possible that the second derivative is undefined. I don't think we have any examples of that here, but it is a possibility. But mainly what we're going to run into is functions where the second derivative is defined throughout the entire function. And then that means that what we're looking for is the signs changing from positive to negative. All right, so here's the function. And we'll take the first and second derivatives using the power rule. And we end up with 6x minus 12. Okay. Set it equal to 0 because this is what we're after. And what we found that when x equals 2, this function has a second derivative of 0. Now, the original function was x cubed minus 6x squared plus 9x plus 30. So f of 2 will be 2 cubed minus 6 squared plus 9 times 2 plus 30. All right, what is that? 32. Now, having said that, though, we still don't know where the function is going concave up and concave down. So what we're going to do is find or test the sign of the second derivative in each of those two intervals. Now, I mean, from the graph, you can see that second derivative, oh, sorry, I wrote backwards. Because we're increasing at a decreasing rate here, as we go up that hill, it should be clear that the second derivative is negative along here. And then it switches to positive here. But let's prove it. Okay, so we'll take the second derivative and we'll pick points in those intervals. So for example, we'll start at 0. And as we expected, it's negative. Okay. Now, by the way, and again, because of the mean value theorem, we don't have to test every single point in that interval. That would be kind of ridiculous. We just need one and we're all set. And then we go to the other side, the interval 2 to positive infinity. and we'll pick 3, for example, and we discover that the second derivative is positive, which is no surprise. Okay, yeah, after that point it's positive. And therefore, not only do we find a point of inflection, but we know that we know the ranges over which the function is concave up and down. Okay, so it went from down to up. All right. And yes, I went ahead and solved. I guess we already did this. So the point is actually 2, 32. Okay, that's that. All right. Now, what we're going to do is discover how to find extrema using the second derivative test. How is it different than the first? Now, remember the way the first derivative test works, just a quick review. Uh-oh, what did I do? I didn't want that. Just a really quick review. So in other words, what we're checking is the sign of the first derivative on either side of our critical points. What we're going to do here is instead with the second derivative, and it'll give us the same results. What we're going to do is this. When we find our critical points, and we simply want to know now, are they relative maximum, minimum, or minima? At that point, if the second derivative is positive, then this is a local minimum. If the second derivative is negative at that point, it is a relative maximum. By the way, don't forget, relative and local mean the same thing. But if the second derivative is 0, meaning it's an inflection point, then we still don't know if this is a maximum or a minimum. And then something else has to be done. That something else usually means we go ahead to the higher order derivatives until we find one where we have either a positive or negative sign. So we're not going to do that right now, but if the test is inconclusive, there are ways we can follow up and continue. We're not stuck, let's say. There are options that we have available to us. But so here's one. Now this is a wacky function. F of x equals x to the 5th minus 5x cubed. Let's use the second derivative test to identify any local extrema. Now look at this thing. Yeah, when it has such, I mean, x to the 5th, it has the ability to have these very strange shapes. So we'll take the first 2 derivatives. And of course, it should be pretty clear that these are the extrema. Here's a case, look at this. We're going to have one of those cases where the first derivative is 0, and yet it's neither a maximum nor a minimum. So let's try this. Take the first 2 derivatives using the power rule. Now, remember, the first step in any type of test like this is we need to know where the tangents, where the flat tangent lines are. In other words, we need to identify all the critical points. So we'll set the first derivative equal to 0. and solve for the, now you notice even the first derivative is a fourth order polynomial. There could potentially be up to 4 solutions to this. Wow. But as it turns out, there's only 3. Okay, so yeah, set it equal to 0. Now, when you have such a very large polynomial like this, large order polynomial, often we can factor out at least some of the x's. So here we have 5x squared times x squared minus 3, each of which we can now set equal to 0. And so we're actually, the 2 solutions, we'll get 1 solution here. And we'll get 2 solutions here. The question is, what are they? All right, well, they won't be that bad because 5x squared equals 0, divide out the 5, divide out the x equals 0. On the right-hand side, we have x. Now, by the way, this time, remember before we discarded the negative solution. We do need it this time because the range of the domain rather for this function is all real numbers. So we've actually got 3 critical points: 0, positive, and negative 3, radical 3. So let's just take a quick look at the graph for a second. So this will be negative radical 3. This is 0. This is positive radical 3. So what we need to know now is, what is the second derivative at those 3 points? Okay. So for the 0, and you probably could have anticipated this, given that this is neither a minimum nor a maximum, the second derivative test is inconclusive because it is 0 at that point. Okay. The other 2, negative radical 3, when you plug that into the second derivative, you get a negative number. And we saw earlier that a negative second derivative means that we're looking at a relative maximum. Okay. At that exact point, this is negative, at this exact, and you can see what's coming down here. It's going to be positive, but and that guarantees this is relative maximum. And oops, I keep doing that. For positive radical 3, you get a positive number, which guarantees that this is a relative minimum. Okay. And yeah, you can put it together in a little chart, and then down here I've drawn the pictures. So there's your second derivative test. Now, whenever you're looking for these points, it's up to you to decide which test to use to identify whether any of these points are relative maxima or minima. Nobody's going to say to you, well, I mean, maybe on a test, but in general, you can use either one of them. All right, so that's what we did in B. Now in C, we've got some more rules. No, I've got to turn that thing off. Here we go. Oh, now I mentioned this several times, I think. I couldn't wait till we get to this topic because it is such a lifesaver. When you have these horribly messy limits, but specifically when direct substitution leads to a result of 0 over 0, and you're tempted to give up, or you're tempted to try some very complex simplifications, as long as the actual substitution leads to 0 over 0, we can use this L'Hopital's rule. And, the first time you see this, you want to say Las Hospitals or whatever. It's not. It's L'Hopital. And what it's telling us is that if we have 0/0 with direct substitution, then we can find our limit by taking the derivatives of the numerator and the denominator, and then we can use direct substitution. And it saves so much grief. You cannot believe this is one of my favorite rules in calculus. It's absolutely, it's amazing how much time and money, well, not money, but how much time it'll save us. So I've been looking forward to this for a long time. So anyway, so it's break time, I see. So why don't we stop for a bit, our usual 15 or 20 minutes to recover. And when we get back, we'll finally get to see L'Hopital's rule. And by the way, if you feel like it, what you could do is go back to our discussion about limits in an earlier chapter and confirm some of those results with L'Hopital's rule. Because there we were trying to use complicated algebraic rearrangements, but it may not be necessary to do that. Often taking the derivatives will really simplify it so much that this is really the way to go. But all right, anyway, we'll stop right here. When we get back, you'll get to see this exciting new rule. And I think you'll agree that it is a lot of fun. Challenge? No, challenge. All right, now let's do this. Let's look at the L'Hopital's rule. Okay, so once again, the way it works is that when you've got a ratio of 0/0, you can use L'Hopital's rule and basically just take the existing ratio and take the first derivative of each function, and then you can try direct substitution. There's no guarantee that it will work at this point, but it's a lot more likely that you'll get a result when you take these derivatives. And so let's look at some examples. So let's say you're looking for the limit as x goes to 0 of 1 minus cosine x over x. Now, you can look this up in Symbolab. Cosine 0 is 1. So you can see direct substitution will get us nowhere because you'll end up with 0/0. So what do? Well, it's possible that there's some simplification we could try. If you look through all the trig identities, it's possible that we could come up with something, but it's really not necessary because all we have to do is take the derivatives. And if that still doesn't work, then we may have to try some substitutions. But by the way, here's what this looks like. And so what we're aiming for is right there, that hole there is actually what we're aiming for. That's the limit that we're looking for. Now, as you can see, though, because the function is converging to the same point from the left and the right, that means that the limit does actually exist. It's just a question of finding it. Okay, so you remember that with limits, even if there's a hole in the function, as long as the function converges or approaches the same point from the left and the right, this is going to be our limit. And you can see from the graph that the limit will be 0 because it's right on the horizontal axis. But how do we prove it? Okay, that's what we're after. Now, I just want to remind you that the derivative of cosine x, and again, you can double check this on Symbolab, is negative sine x. Okay, and the derivative of x, of course, is just 1. All right, so that should clean things up a bit. So yes, you're directly applying the derivative to the numerator and the denominator. And as we've just seen, that's going to give us, now, of course, the derivative of 1 is 0. So you've actually got 0 minus sine x, or just plain negative sine x. And this is 1. And so this reduces very nicely to 0. I'm sorry, not 0, sine x. So you're taking the limit as x approaches 0 of sine x. And now with direct substitution, the sine of 0 is 0. And so we're done. Okay. So again, if you're not sure, let's go back to Symbolab. Our old friend Symbolab. I, of course, now have the advanced version of it. Wait, what was that again? Right, so we need the sine of 0. Very good. And it is, in fact, 0. Yeah, you notice how they're calling it the trivial identity. In other words, there's nothing to derive. It is defined to be equal to 0. Okay, so that's it, then you're done. So, but we knew that already by looking at the graph, because again, the function approaches 0 from either side as x approaches 0 from the left and the right. In both cases, we're approaching 0, but we needed to be able to prove it. And one of the easier way to do that is to use L'Hopital's rule. Oh, nice. Okay, now this next one looks like a catastrophe in the waiting. Oh my God, look at this. The limit is x goes to infinity of e to the 1 over x minus 1 all over 1 over x. So when you take the limit, if you directly substitute, remember the limit as x goes to infinity of 1 over x is 0. Because what's happening is that x is getting incredibly large, and therefore the ratio 1 over an incredibly large number gives us a limit of 0. So what that tells me is that direct substitution would lead me with e to the 0 minus 1 over 0, which is 1 minus 1 over 0, 0 over 0. So in a way, we're out of luck, but yet we're not, because we can use L'Hopital's rule. Of course, the challenge here is that those are some scary looking derivatives. Well, not really. Just as a quick, oh, by the way, here's what it looks like. So as we approach infinity, that means we're going in this direction. And you can see it appears to have an asymptote. It looks like that's 1. It's hard to be sure with the graph, but it looks like we have an asymptote at x equals 1. And if we do, that's going to be our limit. Okay, but let's just go through, check it out. So okay, so here, once again, I'm just showing how direct substitution will give us 0 over 0, so we can feel free to use our derivatives. Okay, so let's start with the denominator. Now, 1 over x, of course, we can rewrite it as x to the minus 1, and we probably should. I think that makes it easier to use the power rule. And based on the power rule, we end up with minus 2x to the, minus x to the minus 2, so that's easy. It's that other one, that e. So just as a quick reminder, what you're doing is you have e raised to not just x, but a function of x, which means that probably the chain rule will get involved here. And that's exactly correct. So I put a little quick reminder here. When you're trying to take the derivative of e raised to some function of x, you end up with e raised to that function of x times the derivative of the exponent. In other words, g prime of x. Okay, so, dealing with the e's, taking the derivatives of e, it's a very simple function to work with. And so, again, since we already know that the derivative, we saw a minute ago, is minus x to the minus 2 power. So in other words, the derivative of e to just e to the 1 over x is going to be e to the 1 over x times this. Because this is g of x. It's e to the g of x times g prime of x. And then, you can rearrange it a little bit. I'm not sure if this is really necessary, but you can write it as negative e to the 1 over x times x squared. If you want, you can write it as hold on. Another possibility is anyway, but remember, we're actually taking two derivatives. We've got a numerator and a denominator. So this part proved to be minus x to the minus 2. And this piece is this. Okay, x to the minus 2, e to the 1 over x. So it looks like these are going to cancel out, doesn't it? Okay, so we can confirm that. Now, once that's done, by the way, we're still not done with the problem because we still have to take the limit. Okay, but as far as the algebra goes, yeah, here it is. So it reduces very nicely to e to the 1 over x, as I've just shown here. Oh, wait a minute. Oh, the negatives canceled out. Okay, so I did something wrong up here. Oh, there was a negative here. I did not copy it correctly. All right, I just want to confirm that. So yeah, so I messed it up a little bit right here. This is also negative. So yeah, so the derivatives give us a result of e to the 1 over x, but we still have to take the limit. Okay, so you can see right here, we're taking the limit. This is the result of taking the derivatives in the numerator and the denominator. Now, as we saw earlier, the limit as x goes to infinity of 1 over x is 0. So this, with direct substitution, you have e to the 0, which of course is just 1. So as I suspected, even though it was hard to be sure from the graph, it appears that in this graph, there is an asymptote at x equals 1. And as we continue to increase to the right, as x keeps getting closer and closer to infinity, the function is getting closer and closer to 1. So the fact that there's an asymptote there means that we've done this correctly. The limit, as x goes to infinity, is just 1, because that's its asymptote. All right. Well, that worked out well. Now, by the way, this rule is more general than you might think. It's not just for cases where we wind up with 0 over 0. If you end up with infinity over infinity, you can also use L'Hopital's rule. So there's, and also you might see this term again, indeterminate. That just means we can't solve for it. Infinity over infinity doesn't have any actual mathematical meaning. Neither does 0 over 0. They're simply undefined. So when we end up with that, we have to do something about it. All right, let's take a look at an example. So now you can see, if you directly plug in the infinity there, if you remember the way when we first introduced limits, this could actually be written like this. Now, in this first case, what we actually end up with is 3 times infinity plus 5. Now, of course, we don't need to make a distinction between infinity and 3 times infinity plus 5. In other words, this is just infinity. Adding 5 to it, multiplying it by 3, it doesn't matter. It's still infinity. And the same thing down here. You could actually write it as 2 lim . So you've got 2 infinity plus 1. It's just infinity. So we got the result we were looking for. Infinity over infinity. And that means we can use L'Hopital's rule. Now, let's look at this catastrophe. Oh, my God. But again, you can see there is an asymptote. Well, I can't really tell for sure what it is from this graph. It doesn't look like it's exactly 1 this time. So, but since there's a horizontal asymptote, that's going to be our limit. Whatever that happens to be, that's going to be the limit. as x goes to infinity, that is. So let's use L'Hopital's rule. Well, this one is especially simple because you can see we've got the two polynomials. Look at that. Three-fifths, and that's just three-fifths. It doesn't matter if we're going to infinity or not. It's just three-fifths. So yeah, if you look at this graph, I knew it didn't look like exactly one. That's the horizontal asymptote. Which implies that the limit as x goes to infinity of this function is three-fifths. Okay. So whether we end up with 0 over 0 or infinity over infinity, we can use our L'Hopital's rule. Now, if it still doesn't help, there's other things we can do. We're not going to do those right now. We're just going to stick with cases where the first derivative will work. But it's still possible you might have to do some algebraic rearrangements to get into a form that you can actually use. And pretty much you should end up with a good result. Oh, wait, did I write the wrong thing? Oh, yes, I did. Oh my God, I didn't. Sorry about that. I was looking at the wrong thing. It's 3/2. Oh my God. It's getting late. 3/2, yes. In other words, it's 3/2, for God's sake. All right, let me fix the diagram. Yeah, 3. All right. I'm sure you just wanted to shout at the screen. What are you doing? That's right, 3/2. Okay, very good. Oh, now this one, it may not be obvious right away, but this one, of course, will also give us infinity over infinity. The log of infinity is infinity. If you look at the graph of the log, it looks something like that. And as x increases, this function increases forever. So we end up with infinity there. And of course, 5x, it's just a straight line. So that's also infinity. All right, so what do? We take the first derivative of each. And here we got a bit of a break. The derivative of log x is very simple. We don't need the chain rule because it's just log x. It's just 1 over x. And of course, the derivative of 5x is just 5. Oh, this will be nice and easy. See now this graph is just log x. By dividing it by 5x, it ends up looking like this. But you can see, well, we'll see how it goes. But so it's a little different than the natural log by itself. So we take the derivative, the ratio of the derivatives. And so yes, the numerator has a derivative of 1 over x. The denominator is just 5. But remember, again, we keep seeing this all the time. And again, that's because 1 over x looks like that. And you can see that the horizontal axis is an asymptote to this function. So that's why the limit is 0. And so we end up with 0 over 5 or just 0. And so, although you can't tell from this, I guess if you could keep looking and watching it go, you can see that it's clearly decreasing. Oh, I didn't even notice it. It shows it right here. Yeah, right there. There's an asymptote. In Symbolab, the red means it's an asymptote. And so that's our asymptote. And that must be the limit. As x goes to infinity, that is. Nice. You can see how simple this is. I like this. This is, like I said, this is my favorite rule. Now, here's the big question, though. There's other potential indeterminate forms. In other words, these are other very messy results that we may encounter, and it may not be necessarily possible to use L'Hopital's in these cases. L'Hopital is for 0 over 0 or infinity over infinity. What about these other ones? Ooh, look at these. They really look pretty bad. For example, you might run into 0 times infinity, infinity minus infinity, infinity raised to the 0 power, and 0 raised to the 0 power. Now, here we sort of have to play this by ear. This is, you can think of these as being done on a case-by-case basis. We may be able to rearrange the function into a form where we can then apply L'Hopital's rule. In other words, if we can somehow find a way to rearrange the function so that direct substitution leads to 0 over 0 or possibly infinity over infinity, then we're good. Then we can just use L'Hopital, but it may not necessarily work out that way. So we have to be careful with these. There are different strategies involved. Just as a hint, though, where we're going with this, whenever you see exponents, like in the last 2 cases, almost without fail, we're going to try to use the properties of logarithms to streamline the results and turn it into something more manageable. So let's just take a look at the first one. So you've got a product. Now here's a classic example. Both of these are functions. If one of them was a constant, then we'd be all set. So what you're ultimately trying to do here is, if it's at all possible, rearrange this algebraically to come up with a ratio. And if it is a ratio, then you just might get lucky and you might end up with a case where you can use L'Hopital's rule. If not, well, you might still be able to simplify it. Okay, it's always good to simplify. Here's one. Now, what's the problem with this one? Well, let's see what happens with direct substitution. Oh, you know what I forgot to do? I forgot to put this into Symbol Lab. Hold on 1 second. I want to see what this monstrosity looks like. Oh my God. Well, you know what? I must say that is a very interesting graph. So it appears that there's an asymptote. Yeah. Well, it's hard to tell what value that is, but there is an asymptote. Wow. Anyway, if you plug in the numbers as they stand, you're going to get, ultimately, it settles down to infinity times 0. Okay, because the limit of x to any positive power is going to be 0. I'm sorry, infinity. If you have 1 over, then you have 0, because you're basically, it's 1 over a gigantic number. So here, we move the 3 outside. This by itself should be infinity. Now look what happens here though. We've got 1 over x squared plus 1. So this is going to give you direct substitution 1 over infinity plus 1, which you can just basically reduce to 1 over infinity, which in turn can be rewritten as 0. Okay, in other words, any constant over infinity is just 0. So, and in spite of the constants, this is your basic form. So here's a strategy that you can apply. We'll start by, moving the 3x squared into the numerator. But then here's where it gets interesting. We're going to divide the numerator and the denominator by x squared. Now, I just want to point out that you could divide by anything, but in this case, x squared will help us because you'll see it'll reduce this to a point where we can actually solve for it. If it doesn't work, you can try other exponents. You could try, for example, just plain x. It's possible too, you could try higher powers, but we'll start with x squared to see if it works. And what is this getting us? Well, you can see here that in the numerator, x squared over x squared is 1. In the denominator, we have x squared, 1 plus 1 over x squared. And so the limit, as you know, of 1 over x squared is just 0. So we end up with 3. These all stay, but this one becomes 0. So look at that. It's 3. Now, who would have thought when we started out that this could possibly be so straightforward? But there you go. So why don't we look at our graph again? And does that look like 3? Yeah, I guess it is. Like I said, sometimes the way they've labeled it, it's really hard to be sure, but it appears that this is 3. And so that is our asymptote, and that must be our limit. Okay. So with this group, you can see there's a certain amount of trial and error going on. We tried x squared, but if that didn't work, we could have tried x to the 3rd or x. So with these other indeterminate forms, sometimes we have to try different possibilities until we find one that works. With L'Hopital, as long as you see 0 over 0 or infinity over infinity, you're all set. Okay, so that's the nice thing. And sometimes our goal in these limits with the other indeterminate forms, like I said, is to reduce it to L'Hopital's rule. So, all right, anyway, I think it's 9 o'clock. I guess we can stop here. I think we had plenty of fun for one night. And then on Thursday, as usual, we'll pick it up right here. We've got plenty more indeterminate forms, and then we have some applications to look at. But lots of fun topics are coming your way. More limits, more of everything, but so it'll be fun. All right, so I guess we'll stop here, and I'll see you all on Thursday.
Professor Anderson?
Yes.
Hi, I just had one question.
Okay.
I just wanted to ask if it was possible to have an extra day to hand in the problem set.
Sure.
I haven't really, thank you. I was gonna say I haven't really had a quiet space since my sister got COVID, so now the whole family.
Oh, yeah. Yeah, it's okay. I mean, it's not meant to be extra, ultra, super rigid. Especially because, it's the summer, it's online, and people are having issues, can have issues. We've got a few people who are sick and have been sick, or their family members have been sick, and then some people are traveling. So it's okay. You do, send me an email and remind me that we had this conversation. And yeah, it's fine.
Okay, thank you so much.
You're welcome.
All right, have a good night.
All right, good night.
Have a good night, Professor.
Okay, good night.